Next topic is the equivalent circuit. So how do you represent the synchronous generator in the form of a circuit so that we can analyze it easily? Now we have seen the expression for generated voltage, right? But the voltage that is actually available at the terminals, this is not going to be same as the generated voltage. So what is the reason for this? We are going to have three different factors. First is the armature reaction. So we have seen this in other machines as well. What is armature reaction? It is the distortion in the magnetic field caused by the current flowing in the armature coils. Okay, so we will see what is this effect and how do we model this in terms of an electrical circuit model. Okay, the next parameter or the factor that we have is the leakage flux. So how do we model the leakage flux? We have already seen this in various machines. Leakage flux we model in terms of an inductor. Now one thing that you need to notice here is how we use the terms armature winding and the field winding. The armature coil here is on the stator, not on the rotor. Okay, if you see in a DC machine, you have field winding on the stator, whereas the armature winding is on the rotor, right? So the generated voltage that we are going to have, that is going to be the armature winding produced voltage, whereas in the synchronous generator, what are you going to have? The field winding is on the rotor, not on the stator, whereas the armature winding, this is on the stator. So as soon as you say armature winding, do not think of it, do not assume that it is on the rotor. It depends on the machine. Okay, armature name is given to that winding which will actually generate the voltage. Okay, and finally the resistance of the armature winding. Another factor is also there, which is the shape of the rotor. So we have seen there is a salient pole or a non-salient pole. Non-salient pole in the sense in the form of a cylinder, right? So this also will bring about a difference. But first we will discuss these three parameters. Okay, the equivalent circuit based on these three parameters. That means we are going to find out the equivalent circuit of a non-salient pole or a cylindrical rotor machine first. Okay, so first we will see how to model the armature reaction. When the machine is not connected to any load, what is going to happen? There will be no stator current. No load implies that the winding is open circuited, right? Implies stator or the armature winding is open circuited, right? This means that no armature current is flowing, and when no current flows, there will be no magnetic field produced because of the armature current. Okay, so no magnetic field due to armature current. So in this case, the terminal voltage that is available will be equal to the no load voltage. Okay, but when there is a load, under loaded condition, this is the no load condition, this is the loaded condition. In this case, what is going to happen? There will be a closed armature winding. So armature winding is closed network. This implies that current flows in armature winding. So that means non-zero armature current. So once the armature current is flowing, then what will happen? It will produce its own magnetic field. Okay, so magnetic field produced due to armature current. So in the first case, the only field that was available, the only flux that was available was the field flux. Here only field flux is present. Whereas here you are going to have field flux plus armature flux. That means the magnetic flux that is produced due to the armature current. So this is what we call as the armature reaction. That is distortion of main field flux due to armature flux. So now if you consider the flux due to armature flux, this you represent as phi AR. This is the armature flux. Now what will be the phase of IA? This will have the same phase as armature flux phi AR. But what about the voltage that is produced because of this armature flux? This is going to be lagging the flux by 90 degrees, right? The flux will lag, the voltage will lag the flux that is producing it by 90 degrees. So EAR lags flux by 90 degrees. This means that it is also lagging the current, armature current by 90 degrees. Okay, so that means you have a leading current here. So you can write EAR is equal to minus J times armature current into some reactance. So this reactance we can represent as XAR. So this is how you model the armature reaction. Now what will be the net voltage that is available at the terminals? It is going to be E net is equal to the generated voltage, we'll write it as EG plus EAR. You can write it again here. This is the actual generated voltage only due to the main flux, due to main field flux only. And this is the generated voltage due to armature flux only. If you add both of them, you are going to get the net voltage. Okay, so that means the terminal voltage that is available to you, E net, is going to be equal to EG minus J times IA XAR. Okay, so how you can model this? If you draw a voltage source here, this is EG. Now EG is the voltage source. If you consider, then you can take an inductor and the voltage that is available here is the net voltage. What will be this voltage? This is J times IA XAR. So that EG is equal to JIA XAR plus E net, right? This same equation only you are just rewriting as EG is equal to E net plus J times IA XAR. Okay, so that is how the armature reaction we are modeling in terms of an inductor. Okay, therefore armature reaction is modeled as an inductor. Okay. Now what is the next parameter? Leakage flux. So leakage flux we have seen, this is modeled as an inductor. What about the resistance of the armature coil? This we model as normal resistance, right? So these will also cause a voltage drop. Okay. So all of the parameters, the armature reaction, the leakage flux, resistance, everything, they will now appear in series. So that means the final equivalent circuit is going to look like this. This is the EG. Okay, so when you write positive here, it means the first half of the cycle is going to be having a positive polarity here and negative polarity here. Okay, so in series to this, you're going to have the resistance. You can represent it as RA, meaning the armature resistance. And next we have the leakage flux. We can write this as XL. So this we can write here as well. And finally, the armature reaction XAR. Finally, this is the voltage that is available at the terminal. So you can write down the terminal voltage that is available. Vt will be equal to Eg, which is the actual generated voltage if there is only the main field flux and no other parameters like the resistance, leakage flux or the armature reaction, minus the armature current. If it is IA into RA minus drop across the leakage fluxes IA into J times XL minus IA into J times XAR. So one important thing that you have to remember always, this is the per phase equivalent circuit. Okay, so we are talking about the per phase value for each of the value. The stator winding, all in all, it will have how many phases? 3 phases. We are talking about only one phase here. Each of the 3 phases are going to look similar except for the phase difference, 120 degrees phase difference in case of balanced systems. And another thing that you can see here is we have 2 inductors in series. So what will be the equivalent inductance or the equivalent reactance? This is going to be equal to the leakage reactance plus the reactance due to armature reaction. So the sum of both of this we call as the synchronous reactance. Okay, so that you can express the equation, the terminal voltage as Vt is equal to the generated voltage, or you can say the no load voltage, minus Ia times Ra plus J times Xs. Okay, so if the armature current is 0, terminal voltage will simply be equal to the generated voltage. Now this combination Ra plus Jxs, we write this as Zs. We call it as synchronous impedance. Okay. We will now try to draw the phasor diagram, okay, for various kinds of loads, right. So that means this was the equivalent circuit that we have derived, right. This is the generated voltage, we will take it as E, or you can write Eg. This is the armature resistance and the synchronous reactance, and the armature current you can take as IA. Now here you are going to connect a load. Now this load can have a unity power factor, lagging power factor or a leading power factor. What is meant by unity power factor? This is also called as UPF, okay, abbreviated as UPF. So this means that the terminal voltage Vt and the armature current will be in phase. Vt and Ia are in phase. That is when we call as unity power factor. What is meant by lagging power factor? When the current Ia lags the terminal voltage Vt. And what is leading power factor? When the current leads the voltage. So it is the relationship of the current with respect to voltage. Okay. So first, if you take unity power factor loads, in that case what will be the phasor diagram? So always we take the terminal voltage as the reference phasor. So this is VT. Now where will be IA? IA will also be in phase with terminal voltage. Okay. Now we know that EG is equal to the terminal voltage plus the current into synchronous impedance, or RA plus JXS, right. So now we have the phasor VT here. Now what is the phasor IARA, the drop across resistance? This will also be in phase with the terminal voltage, right. So this is going to be IARA. Now what about this J times IAXS, right? So IA, whatever phase is there, into angle 90 degrees is there. So that means the drop across the reactance XS is going to be 90 degrees leading, right? So that is the characteristic of the inductor. The voltage will be leading the current. So here you have J times IA into XS. So what will be the actual generated voltage now? This is EG. You can also call this as the no load voltage. Next, how do you draw the lagging power factor phasor diagram? Lagging power factor. Okay. So once again, the terminal voltage you will have VT, the reference phasor is angle 0 degrees. Okay. Now lagging PF means the current will lag the voltage, the armature current will lag the voltage. So we will take the lagging angle to be phi. Okay. Now what will be the drop IARA? IARA will be in phase with the current. Drop across the resistance will always be in phase with the current flowing through it. So the drop across resistance, you can take, these two are now parallel. Okay. So this is IARA. Now what is the drop across the reactance? Synchronous reactance, it will be 90 degrees leading with respect to the current. So that means since these are two parallel, you will have a 90 degree phasor here. Okay. So this is 90 degrees. J times IAXS. Okay. So now what will be the generated voltage? This is going to be the generated voltage. And finally, the leading power factor. Here also we are going to take the terminal voltage as the reference phasor. So this is VT, angle is 0. Now IA is going to be leading. So let us say this is phi. So the drop across resistance will also be parallel to this. So this is IARA. Right. Now what will be the drop across the reactance? Synchronous reactance, this will be 90 degrees leading the current phasor. So that means it will appear here. So this is what you are going to get. J times IAXS. Okay. So now what will be the generated voltage EG? It is going to be like this. So you can see that this generated voltage can in fact be lesser than the terminal voltage if the right conditions are present. Okay. So these are the phasor diagrams for various power factors of the load. Okay. When we are talking about the power factor here, we are talking about the power factor of the load. So one important point that you get from the phasor diagram is how to represent the generated voltage in terms of the load power factor. Okay. So if you draw once again we will take the example of lagging power factor. Okay. So that means this is the terminal voltage. Say this is the armature current at a lagging angle of phi. So you are going to get IARA drop here, and at 90 degrees you are going to get J times IAXS. Now this is the generated voltage EG. Now here what you will do is you will drop a perpendicular from the voltage phasor, terminal voltage phasor. Okay. So this is now the perpendicular. Now you extend further, and this IAXS line if you extend, this will also be perpendicular. Why is that? Because this and this are parallel and this are parallel. Okay, so all of these angles will be 90 degrees. Now this triangle that you have here, this is forming a big right angle triangle. So what is it? Here O, if you take, this is A, B, then OAB is a right angle triangle. Now further, if this point you take as C and this point you take as D, then you can write OB whole square, which is the hypotenuse of this triangle, right? OB whole square will be equal to OA whole square plus AB whole square. Now what is OA here? OA you can write as OC plus CA. Now what is OC? So you can see in this right angle triangle, this angle is phi, this hypotenuse is VT. Now what is the value of OC? This will be the horizontal component of VT. So that means VT cos phi. So you're going to write OC is VT cos phi. Then what about CA? CA is nothing but this. This is a rectangle, right? So the opposite sides are equal. So IARA. So this will also be IARA. So you're going to get IARA. Now what about AB? This is equal to AD plus DB. So now what is AD? AD will be same as this here. Okay. So you can take this point, you can take as E. Now AD is equal to CE. So what is CE? Once again in this triangle, if you take, this angle is phi, this is the hypotenuse VT, this is going to be VT sin phi. So this is VT sin phi. Then what about DB? This is nothing but the drop across the reactance. So you're going to get IAXS. Okay. So now you have OA and you also have AB. So you can find OB whole square. So what is OB whole square? It is nothing but the generated voltage EG. So EG square is equal to VT cos phi plus IARA whole square plus VT sin phi plus IAXS whole square. Okay. So if you take the root, that means instead of EG square, then you are going to get root over this quantity. Okay. So this is how you express the generated voltage when the load is lagging. For lagging load. Now what happens in the case of UPF? UPF is simply meaning that cos phi will be 1 and sin phi will be 0. So you can write EG is equal to VT cos phi plus IARA whole square plus IAXS whole square root over this entire value. Okay. So this is the expression for the generated voltage for which load? UPF load. Now what happens for leading load? So if you take this as terminal voltage and the current is leading, right? So we will take this angle to be phi. Now you're going to have IARA here. This is parallel to this. Now what will be the drop across the resistance, the reactance? This is going to be like this. G times IAXS. So you're going to get this as the generated voltage. So here also you're going to use the same funda. You're going to drop a perpendicular from this terminal voltage onto this current phasor. Okay. So now this is 90 degrees. Similarly, you extend this line. Okay. So this is also 90 degrees. Now you can see that this triangle, this if you take O and this if you take A and B, then OAB is a right angle triangle. And you can take this point as C This point you can take as D and this is E. Okay. So you have OAB is the right angle triangle. So that means you can write OB whole square, the hypotenuse, is equal to OA whole square plus AB whole square. Okay. So now what is OA? This is equal to OC plus CA. Now what is OC? This is a right angle triangle. Now this is VT, this angle is phi. So what will be this? OC will be VT cos phi. So you're going to get VT cos phi. Now what about CA? This is same as IARA because this is a rectangle. So you're going to get plus IARA. Okay, so this is OA. Now what about AB? So you can see that AB you can write as this entire length AE minus BE. If you write, you will get AB, right? So AB is equal to AE minus BE. Now what is AE? This is the CD line. So from this triangle you are going to get, this is VT, this is phi, so CD will be VT sin phi. So VT sin phi. Now what about BE? BE is simply the drop across the reactance. So you are going to get minus IAXS. Okay. So these values you will now substitute in this. Okay. Now what is OB here? OB is simply the generated voltage EG. So you are going to get, therefore, from this equation you are going to get EG square is equal to OA is VT cos phi plus IARA whole square plus AB is VT sin phi minus IAXS whole square. Okay. So this equation you can write as EG is equal to root over VT cos phi plus IARA whole square plus VT sin phi minus IAXS whole square. So this is the expression for leading load. We have already seen for lagging and UPF. Now this is for leading load.